Okay, so we have a problem here about a blocks of mass m that is seen accelerating from rest down an incline that has a coefficient of friction mu. That's what that symbol is. And is an angle theta from the horizontal. I'll also highlight mass m because that's a given. And then I guess in green, the actual question: how far will it travel in time t? Okay, cool. So let's go ahead and draw some pictures, because that's always the fun thing to do. We'll start with just a picture of what's actually happening here. It's not the best block or the best ramp, but it'll do. This is an angle theta from the horizontal. And we start here, and eventually we get to here. This is our block of mass m, and we can see it's obviously accelerating this way. So that's our first drawing. The next thing I want to do is, well, we'll continue drawing, but let's go ahead and define our origin and our axes. So what I mean by that is if we were to draw a three-dimensional, right, x, y, and z, the origin here, let that be, boom, right from the start, which we'll talk more about in a second. The other thing I want to do is tilt the coordinate axis because, well, we can see you have a few forces, and it might be easier if we label our forces first, but we see it's accelerating down the ramp, so we kind of want to line up our axes so that one of them is pointing in the direction that our block is moving. It also kind of helps with solving some of our unknowns, but basically what I'm saying is let's let this line up here. And then perpendicular from that, I guess I'll do that in orange. It's kind of like our Y. I think I have orange here. That's like this part. And there's nothing happening in the Z direction, obviously. So let's draw a free body diagram next. I'll do it right here so we can kind of see. So the way I like to do this is I like to start with non-contact forces. So obviously there's no like E field, but there is gravity working on it, right? It's kind of pulling it down, something like this. And that's usually denoted the weight force exerted by the Earth onto the mass, which we know is just mass times gravity. And if we were to make a right triangle by dropping a perpendicular right here, this angle is the exact same as that angle. And you can kind of work that out from a geometry point of view if you'd like. Let's see, what other forces do we have going on? Well, we have a normal force. We have a normal force that is from the ramp pushing back up on it. And we have force I'll call friction, opposing motion. Cool. Let's write down our givens. We're not given any values, but it's kind of implied that we know these. We know the mass m. We know that at time 0, it's from rest. We know that since there's no change, this is also 0. We know mu. And we know theta. And then while we're at it, looking for, sometimes helpful to make note of what you're actually looking for in the end. We're looking for x as a function of time. So we drew some pictures, we wrote down our knowns and our unknowns, and now we can start working with equations. So I'll write down Newton's second law, generally speaking. Sum of all forces is equal to mass times acceleration. And acceleration is the second derivative of position. So let's break this down in every component. We'll start with the z component, which is the easiest because I'll go ahead and write it out for us. So the sum of all forces in the z direction is mass times acceleration in the z direction, but we said acceleration is just the second derivative of position. Well, there's no forces, and there's definitely a mass, so this has to be 0. Well, that was kind of pointless, but it's okay. Next, let's look at the y component. Hopefully it just kind of gets you familiar with the equation. So the sum of all forces in the y direction is mass times acceleration. Well, the block isn't accelerating in the y direction, so we know this will be 0. It's not bouncing up or down, it's just going down the slide. But unlike the z direction, there are some forces acting in the y, right? We have a positive normal force minus this component of gravity, which, doing some right triangle trig, is just the hypotenuse, mass times gravity, times adjacent, cosine theta, equals 0. We don't know normal, but we know everything else, so just adding mg cosine theta to both sides, and now we know our normal force. Well, let's go ahead and look at the x components. X component, there's not multiple. The sum of all forces in the x direction is m times the second derivative. Well, there's two forces acting in the x direction, right? We have this guy, which is positive, and this guy, which is negative, because while we're at it, that's like our origin. So what do we have? Well, we have the component of gravity, which will just be mg, the hypotenuse, opposite, so sine theta, minus the force of friction equals m x dot dot. But we know the force of friction is the normal times mu. So it's really mg sine theta minus the normal, which is mg cosine theta, times mu equals mass second derivative. Well, the masses here drop, and I can factor out a g. So g sine of theta minus mu, I'm going to move that out front, cosine theta equals acceleration. Parentheses. But we don't want to know acceleration, we want to know position. So this is a pretty easy differential equation. These are all constants, so that I can factor that out. And I'm basically just integrating dt, which means I just slap a t out front. I'll put gt, sine theta, minus mu naught cosine theta, equals velocity. But what about the c constant? Well, for our givens, because we're starting at rest at time 0, right, we could substitute that in. We could put a plus c here, right? Put 0 here for your x, 0 for your t, and then what is c equal to? Just 0. So I kind of just went a little quick there. This is velocity, so to get position, let's integrate one last time, right? And we will get 1/2 gt squared times sine theta minus mu cosine theta equals x as a function of time. And the same argument for the c there. And there we go. This equation will tell us exactly where the block goes. So just to summarize, we drew a picture. We drew 3 pictures, which is fine. We listed out our givens and what we're looking for. We made note of important things like Newton's second law and the definition of friction. Then we analyzed all 3 components. We found an unknown in one of our components, plugged that into our other component, did a little bit of algebra, did a little bit of calculus, and there we go. That's all you had to do.